So I have several disclaimers. First, so I have before CSCS, I have been working at Google for many years, and in Google they have quite detailed style guide about C++ usage in the company. And it's quite good, quite detailed, and very useful. But the only thing that Google Style Guide says about generic programming, don't use it at all. So just instantiate your template if you have if you with a standard library or other libraries that provides that the Google code base provides, but don't don't create templates on your own. And I suffer a lot from this rule. Of course, I did a lot of generic programming in Google, but each time you do it, you violate the style guide, and you have you have to grant the special permission to do that, to prove that your utility that you're doing is really useful and unavoidable. And if you think about this style guide, it's basically make a lot of sense. And this is because, well, it's the most powerful technique in the C++ in the C++ language, and you can do a lot with that. And also you can mess up a lot, and you can harm the code base in unpredictable way, and really highly templated and generic code is expensive. There is trade-off. If your code is have no runtime overhead, it's not for free. You pay the price of the maintenance, and also all design flows are very painful in this area. So if you in general, if you can avoid using advanced techniques, probably it's better to avoid. Just you have to have strong use case for doing generic programming, and to do it right. And of course, you need to do it right to reduce the cost of maintenance and the usage. So, and this is this talk about how to do the right design, how to do it right. So let's as we already know from the STL concept, are used to pass the to define the requirements for the template parameters. So let's build the library that will use the object like that. it's easy to understand what it does. It has next method, done, and get, and you can use it something like that. You can iterate with the next, check the end of your sequence with done, and you have the getter of the current state. Basically, this is one of the way to represent the stream of data. So many people name this kind of thing iterator, but we already have iterators in STL. Then let's name it cursor. Okay, it's pretty easy. The fact, please note that I passed this cursor to the dump function by value. It's not because I'm lazy. This is because this function want to own the cursor, because it basically empties it. It spits the data to standard outputs until the cursor is done. Yes. So and in principle, I can pass this cursor by by reference, but it doesn't make much sense, because you after the data is dumped, you cannot do anything with this reference. With this cursor, it's empty. Well, let's see how we can model this concept. For example, we have file, just a file. And we use C F open function to open it. Let's this class implement the cursor that that outputs character by character from this file. Well, there are a lot of nuances here. So I use unique pointer to hold the resources. But this so basically I need to hold a file pointer, and at the end I need to close it. Yes, and I use for resource management unique pointer with the custom deleter. Here fclose has such a signature that it can be used as a custom deleter directly. So and I don't need because I delegate resource management to unique pointer, I don't need to have destructor here. It's already the data, the file will be already will be closed by unique pointer destructor. And another thing that I use here is optional. It was not mentioned yet, but optional is the C++ 17, I think, extension, and it holds the data or nothing. And you can query the data by dereference operator, and you can use implicit bool conversion to check if data exists in this option. So this class does the thing, well, and more or less trivial. So one thing about this cursor, well, there is no move constructor and copy constructor defined, no destructor. But what do you think? Is it class copyable or not? It is not, yes, because so the default copy constructor is deleted because we have the member functions that is not copyable, but it still has default move constructor. So this is important knowledge about our cursors. We want them to be only to be not copyable, just movable, because, well, in our this is the real case. So we probably want to use cursors like that fetch the real data, and we don't want this guy to be copyable. Why? We don't want to duplicate the stream.
Nico, back to the slide. There is also, in this slide, there is also another C++ 17 feature, which is in the if statement. You can define the variable there. You get int c equal something. And then you can use c inside for the conditions. This is also a C++ 17 feature. Before you had to define the c outside the scope, get the variable and check it out.
Basically C++ 11 feature.
The one with the semicolon, like
no.
14 probably.
No, 17, yes, 17.
I think
right.
17. But
yes, with the semicolon it's 17. But it's nice. Yes, the code is still concise and easy to read. Okay, we can do another more simple model. For example, this cursor just implement the infinite sequence. Yes, so each next just increment the value within it. This code compiles. Why? Because of template deduction. We have this constructor that allows us to skip the angle brackets. But what happens if we will run that? Well, it will be infinite loop because then we have this loop condition, and for for our case, done is always false. So we will continuously dump integers. So it's not what we want. We want it's not what we want. We want something like that. We want to have some function. Let's name it take. Yes, it takes the number of elements and the cursor. Well, let's implement, and now it should work. Yes, if we will have this function, and this function will create another cursor that will use the underlying cursor as an input and stop the stream after we expose 10 elements. Let's implement that. So we will have count is basically countdown, and we for done implementation we just use this countdown. Next we'll decrement this count and also call the underlying input cursor. And get will just delegate. Yes. And now it works. So like that. Because we have this, we still have this template deduction, and take is actually not the function but a type. Yes, so we just create the new cursor here. Note that we move the cursor from the constructor to our class here. Yes, and we take it by value and move it in. And by the way, this is a pretty common idiomatic way to deal with move-only objects. So it's usually more convenient and not to define move so constructor from the R value reference, but define it by value in this case, because this constructor can be also used for the copyable objects, and it can do copy if you want. But for the move only, it will still do the right thing. And you think for example, if you do copy, yes, you still need this copy because your class should own the cursor, yes. And there is no performance degradation if you copy, for example. So now let's bend a little bit this take. Let's rename it to take cur and introduce the function that will take integer and return a lambda that takes one cursor in and returns another modified cursor. So that the call will look like that. So we first produce the new cursor. We first produce the function, the functor, and then we apply it to the numbers from. So do you understand what is going on? Our now take returns a function object, lambda. And this brings us to another important concept. Let's define the concept of the cursor algorithm. It will be any functional object or function, any functor that takes a cursor and returns another cursor. Well, and this abstraction is useful because many useful things can fit in it. For example, if we want filter.
You have a question?
Yeah. Sorry for the previous slide. The const expr that was also explained yesterday. Can you say why are you using that keyword there?
Well, just because I can, but in fact this the object that is returned here, it's really tiny. It's just an instance of our algorithm that is bound to the number 10, to the desired number, how many elements we want to take. Yes. So, and we easily can instantiate this in compile time. Well, we cannot use it in compile time, but we can instantiate it. And
I have also before you were get was returning const ref of the type, and now you are returning decal type auto.
yes.
New comment on that.
This is yes. This is kind of important. What decal auto is here. So basically the intent is to delegate get to the implementation, to the input cursor, and we want to delegate the return value as well. If we will just use auto, it will cast any reference to the value. It's not what we want. If we will use auto const ref, we can do that, but it will be it's just less general pattern. Because if underline get for some reason return value, then we will end up with returning stale reference. And now with decal auto, it does correct delegation. So returning back to this new concept, well, we can do a lot. we can produce, we can do filter, for example, that just takes input cursor and filters the element according to the predicate, like in this example. We can do transform that takes some factor and applies it to each number of input cursor. We can do moving average and a lot of things. And what is good about that approach? It is composable, and this is a very important feature when you design the library. So you should try to design an API in a way that it can be so that the parts can be composed to each other. For example, well, we can imagine that we can the user can organize his pipeline for in that way. So the user needs to process some input data and input data and finally produce an output. And the data has a stream nature, and we can decompose it to several to several stages. Yes, first we filter according to some predicate from the parameters. When we do this, we take n elements, we do that, and then we filter again, for example. Yes, and we can pack it into another into another function that in its turn will be the cursor algorithm. Yes, so it takes a cursor, and because it returns filter, it returns a cursor. Well, this is how it can be used. Well, it's nice, but a little bit awkward because, well, looks like Lisp, isn't it? A lot of braces. Well, we can do better if we will have compose function. What? What we want to do is to and basically what you see here is the function composition. So we take one function, so we apply we pass the result of one function to another function, yes? Function composition. And if we will have the function that will do this composition, the result looks nice, isn't it? At least there are less parents. Okay, let's try to do that. Here's the full working definition of this compose function. What does it do? So first, it takes functions and returns composed function. Now we need to define this composed function. Here it is declaration, it's not definition. Now we want to define this function for in the case where we have two of them. Yes, what does it do? It provides call operator, and we just call composition of f and g. Note that we use forward. Yes, for perfect forward, and it's clear. Now this is the general case when we when we have first function and other functions. What we do? We compose the first function with the composition of the rest. Well, and we just inherit, yes, from the two from the composed of the two elements. And so operator is in place. So what we want to do? Sorry. You can note here that we need to be used in compose function. We need to have constructor from the functions. Yes. So this constructor we don't even need that because for the two function case, because aggregate initialization will work for us. But for the generic case, we should provide constructor. But it's obvious. Yes, we take first function and other function we will delegate to this composed. That's it. And it works as intended. Well, but probably we want even more. We can use pipe syntax, like in bash scripts, for example. Yes. Here is our use case rewritten with the pipe. And by the way, we want also our simple use case also to be able to read, to be able to write with the pipes. Please note that we use here the namespace. I can explain why. We are going. So to implement this pipe syntax, we need to overload globally pipe bitwise OR operator, yes, and it's and we cannot do this overload for just it for all, because it will be too intrusive. So other code can suffer that want to use this bitwise OR operator in other ways. So we want to limit the scope, and then the pattern is that we implement this operator in the pipes in the pipes namespace, and then we expose this namespace in the places where we really need it. So what we should do with that to implement this pipe? Okay, if function, if we have xf and function, it should be x here, and fx evaluates to something valid, we should return fx. So this will be equivalent to the function call. And if not, then we want to do function composition, basically. Let's do it, and that's it. So we use std enable to distinguish between two cases. So let's read it. So if f is invocable with x, this operator got enabled. Operator does the following: it delegates the argument to the function. It calls the function with the arguments and delegate the result. If it is not, we do function composition. We return a functor that does composition. Here, we use another feature of the another feature that was not mentioned. We move our stuff into the lambda with that syntax.
I think there's a typo in the code. You say template class X and then use arg. I guess what you want to use X also in place of arg in the fourth line.
Wait, where?
There, where your mouse is, right on the left. The type of arg is arg, but then you're using X on top. So that is a typo. It should be either X should be named arg or arg should be named X. Okay.
Yes, sure. This should be.
You have also another question.
Sorry.
Is it mandatory to have that order or parameters in the template definition, like xf instead of having f and x?
Because it is not mandatory, because those parameters are deducible. It doesn't matter. But
you have the pipe, right? So the argument on the left of the pipe has to be arg, on the right of the pipe has to be f.
Yeah, in the arguments, but in the template I can.
In the templates you can swap them.
Okay.
Yes. And yes, let's focus a little bit on enable if here. How it works? So this enable if t is just an alias. It expands to type name std enable if blah 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 and the end time. And and this expands this v suffix means that it's also an alias that expands to the value at the end. But this works as follows. If this condition is true, then sphenaya evaluate the whole that thing to this parameter, to integer. And we have default value. We can write 0 or 42 doesn't matter. And we don't use this parameter directly. And, but the signature will be valid. If it's not, this enable if it will fail to evaluate, yes, and this operator will not be instantiated and will not participate in overload resolution. Okay, so now we have this shiny pipe syntax, and we can try to do that. Well, do you see any compile? And the recall dump is defined as that. Do you think it will compile? So the answer is not. Why? Let's try to explore what dump is. We can try to get Jekyll type of dump, and we will fail because this is not a type. This is not a value. It's just something that doesn't have an. So that is kind of useless in other context. It's just a template function that we cannot. The only thing that we can do with template function is to instantiate it. That's it.
So is this then an incomplete type?
No, it's not a type.
It's not a type.
Yes. It doesn't have a name, so it's not a type, it's not a value. Okay, so we can overcome that. How? Let's convert dump into a value. Now, dump is a lambda function. And in C++ 17, we have this, we can apply inline to the values. And we do,
you can do this just because you have the template lambdas. Otherwise, do you have any other way of doing it?
Sure. So everything in this talk you can do in C++ 11, for example, but you have to do more work, and the code will be not so concise. And in this case, you should define the dump type by yourself manually. You should write the struct that with the template call operator, and that's it. And then declare the dump variable of that type. Is it clear?
So I have to create a template struct to mimic the functioning of the template lambda. As
Mauro said before, lambda can be thought as a value of the compile generated class, yes, that have template operator. But nothing stops you to do that manually, and it will be the same effect. Okay, so what's the lessons from here? Generally, templates are not the first-class citizens of the language. If you values are better. If you this dump value, it acts actually. It does everything that template does, but additionally, it's a value. Okay, so let's assume we adopt this cursor library and we want to use it, and we write a big application that do translation from one human language to another. And the interface that we are going to provide is cursor focused. Yes, we just have translate function, we specify the language, and we want to return the cursor algorithm. Yes, that takes one cursor of characters and speeds another translated cursor of characters. Yes. Well, what's the problem with that? So let's assume that the implementation is very complex. We have to do machine learning for we want to fetch data, and we just want to compete with Google Translate. Yes, so it's complex, it's big. Okay, so the problem here is that this interface forces us to have all our implementation in the header because of return value. That have auto in it, so it cannot be placed just in CPP file. Yes. And it's bad because so in some cases it's acceptable, but in our case it's not what we want. Yes, because we want a clean interface and we want it to be exposed. We don't want compile errors to be exposed to the user. So there is a solution on that. Let's say we have this special class named any cursor, and it represents any. So it has parameter, the type. Yes, it represents any cursor of that type. Well, it's like a std function. Yes, you can place an std function any functor. Yes, of the given signature. Let's do the same with the cursors. Yes, and in this case we just define the type that we want to return from our translate function. Yes, we basically want to return the cursor algorithm. Yes, but it's a function that takes a cursor of char and returns the cursor of char. That's it. And now this is the concrete classes. Yes, we instantiate it with char, so we can place it in the header and place implementation in the other translation unit. So
here you're paying the overload of the standard function.
No, it's not an overload.
No, the overhead.
Sorry?
Does it have any overhead?
Yes.
Because of the standard function.
So, so this technique is called type erasure. Yes. So for example, think about the standard function. We pass any functor we can initialize a steady function with any functor that potentially can have type. And after this initialization, it can be used, but the steady function doesn't inherit the type from what it is initialized. So it erases the type. And here we want to do the same with the cursor. And basically, now I can explain how to do this. Yes.
I'm a bit lost. Can you just explain the problem again with the implementation that has to be
Okay, so the problem is that this implementation returns outer type. Yes, and this outer type is inferred from the body of the function. You cannot place. You can, in order to use this translate function, compiler should see the body, because otherwise it doesn't know the signature. And this means that the usage of this function should be in the same compilation unit as definition. You cannot avoid that. And this is the way to avoid that. We just force translate to return our type that where the type is erased, basically. And to do it, we need to implement. So we already have type erasure for the functor, but now we want to implement type erasure for the cursor. So what type erasure? So what it should be? We should have a class that also models the cursor concept. So it should have done, get, and next as required. But and also we should be able to initialize that, to construct it from any cursor of the given type. So what we do, we internally form the runtime interface with done, get, and next method. And here we use this t parameter that is passed to any cursor. Yes, in this case it's a char. And we store in the class the unique pointer to this interface. So, and when you we just delegate to this implementation, we delegate the cursor method to this implementation, and this is the pure interface. All methods are virtual. So to make it real, we need to have specialization, yes? And this specialization is templated for the concrete cursor in an obvious way. What happens in the constructor? We take a cursor. We create an implementation of that. This class, impl, depends on the cursor. But we place it into the unique pointer. of the interface, not the implementation. And we still can use all the methods because they are all virtual, yes? But at that point, we no, the templated is only constructor. After we leave constructor, we lose the type information. Okay? Any questions on that topic? Okay, good. Okay, let's assume that we have we use our cursor stuff, but we in our project, but we have collaborator project that have very similar similar notation that but the names are different. And what we want is to use our stuff with those cursors. So obviously it doesn't work because, well, here all methods are in capital. Well, what we can do? Oh, well, we can write a wrapper, yes, that takes the cursor defined in another API and to convert it to our stuff with done, next, get, written without capitals. This will work, but it's kind of annoying. We have to remember that we need this wrappers everywhere. Can we do better? We can. Let's do another yet another indirection. Let's define. So we have three methods that forms the concept. Yes, and let's for each method let's define the functor that delegates to for example, done will delegate to cursor done. And cursor done we will define as we have before, car.done. And the same is for other methods. And now we will place it into our private namespace. And now on we will use this cursor done. We will use those guys to access to the concept members. It's almost the same that we have before. But what it can give us, let's see. Here we define all this stuff for the cursor from another API. And now it magically works. Why? Because of argument-dependent lookup. Let's see what happens. in our dump function, we execute this done. This done is about to call cursor done. Now, this is cursor done. It is not so there is no namespace specified. So compiler will go and will perform argument dependent lookup, and it will see that cursor done is implemented in the namespace where this numbers from is defined. And it will pick up that. What happens if we're dealing with other with our old stuff? Everything will work as before, because we have those callbacks. If we fail to do argument-dependent lookup, we will choose those that are close to the function in the cursor namespace. Yes, and this is it can, but this is an important technique, because we now have we define basically two interfaces for our concept. One interface with cursor semicolon, semicolon, next, done, and get is for the algorithms that are used with the cursor. And all implementers of the algorithms, they can have, they should use that. For the cursor model, for the concept modelers, we have another interface. It's here. It's indirect, but it's here. So the modeler should implement this cursor done, cursor next, cursor get. Or if he don't, we will just use the default implementation.
Why are the fallbacks not inline const exp? Well,
Their callbacks are templated, so they don't. So so inline is implicit because every templated function is inline, and const export doesn't make sense here because, well, so this function is so okay. Let's return back. No, but maybe in this slide here with this done. Yes, this is it's an empty object basically. Yes. And this why const export makes sense here. We can instantiate it in compile time, but for those okay. So there is one more thing that matters. We note this guy. We manually specify the type here. We can do without this type, but we do that. Why? because we want sphere work for us. If we will not do that, and the user is not implementing anything to do done, then this function will not be instantiated. Otherwise, if we will remove that, in that case we will have compiler errors that will point to this cursor down. This is not desirable, yes, because, well, it's not our problem. User forgot to specify how to do done, yes? That's why we need this Jekyll type here. Okay. So now see what we after we have this formal definition, we can finally formulate what the concept is. Yes, just so we have those rules that are quite complicated. So we to implement the cursor, user either should provide cursor get function invocable by IDL with the given signature, or it has it should have or the fallback should be triggered with get function. Yes, and other rules for other cursor methods, and this kind of interface, it's even more it's even more rich than the runtime interface, because we support some alternatives. For example, it's not so it's the next. For example, we can we can have some concept method to be implemented as with the IDL, and some will go to fallback, for example. Yes. So let's consider another challenge. Suppose we have yet another code base that want to use our cursor stuff, and this code base is written in C++, but well, in Java style. So it's the same pattern. It's a cursor, but it has virtual functions, and it returns some entity, and the entity has a lot of methods with the dump to value to stream. So in principle, and we have this. How Java programmers do, they have this builder that builds the stuff, yes, builds the cursor, and it returns a unique pointer to the cursor. Well, and we, in principle, these things, we have enough information to use its. To use this stuff as in our context. Yes, we can try to do that, and we fail. Why? Because build. We can try to define or we can try to repeat our success here when we just do these concept adaptations, but we will fail anyway, because this build function returns unique pointer, and we don't accept that. So we accept this our stuff to be the real object, not unique pointer. So what we need to do, we need to yes. So here I explain how we will try to adapt this. Yes, and we will still fail. We can try to dereference this unique pointer and try that. This also will not work because this guy, iCursor, it's not even movable. It's an abstract class. So what should we do? Let's focus on the get support, get method support that we have in our cursor stuff. This what it was before, but now we significantly enhance that. So we will do the following. As before, get will delegate to cursor get that will be available by ADL. But cursor get will delegate to yet another function, dispatch get. And we will have several dispatch gets. They all have additional parameter rank. Let's see what it is. Here is the definition of the rank. Rank is templated by integer, and rank 0 just struct. Rank and other ranks, for example, rank 1 inherits from rank 0. Rank 2 inherits from rank 1, and so on. What happens? So we call dispatch get with rank 2. Rank 2 is a better match. If this function is, if this function exists, we will choose that. If it doesn't, it can happen because of this part that triggers Finai. We fall back to rank 1 definition. If this fails to instantiate because of Finai, we go to dispatch. We go to rank 0 definition. So this is our infrastructure, and now what we are going to do. Well, if we observe that our stuff that we are passing to the function has the reference operator, it's a reference or it's a smart reference or whatever, we will call cursor get on it. So we just do the reference. Yes? Otherwise, we do we call but it can happen that we have so that our function is a pointer, but it has get method. Then we do the get. Yes, it refers to the case when we do our native stuff and pass it as a unique pointer. Yes, or some pointer. And otherwise, we can we do our usual callback. So this works. So it's not very. It's not very simple, but it's important because this complexity is hidden for the user, and the user can benefit from the flexibility of our library. We can pass, we extend the notion of our cursor. So now cursor can be defined in various ways. It can be unique pointer of the cursor. It can be cursor with method in it. It can be something without method but with standalone functions. So, and now we can using this rich definition of the cursor, we can do some formal, some type traits, yes, to help user to define, to figure out in compile time is the object satisfies the cursor concept or not. So well, and so first of all, it's very useful to use value type helper. Yes, it will take a type of the cursor. It will apply. It will figure out the type that cursor get returns and do decay. For example, we can figure out that the value type of the file cursor that was defined before is a char. And now we can do the big stuff. We can define the is cursor predicate. So what we do here? We define it in that that it is false in general, and we have also additional template parameter. Well, by the way, I use class instead of type name because it's much shorter. Three characters, and I use template code a lot, so I benefit from that. And also, we had these techniques before in Mauro's presentation, and I don't want this parameter to be named at all because, well, I don't use this name. Why? This is to save some typing. And for cursor, we just we enable this specialization that is true basically. In this case, if cursor is move constructible, if we have cursor get. And we don't care what cursor. Sorry, cursor next. We don't care what cursor next return. That's why we have this void there, and we just check if it voids. It's dummy, but we cannot avoid that because a template language itself it's lazy and pure functional, and we cannot. Well, we we can. That's why we have. So we basically should return true here if cursor if this type exists. But okay. Now we specify that we should have cursor get that takes const that takes const reference, that is L value reference, and cursor down should be convertible to bool. That's it. So we can do more metaprogramming stuff. For example, we can define the predicate if cursor of some particular type, and also VE versions of that. But well, let's left to do here. So now we can. So this is all works, but we need a unicorn. We also want our stuff to be used in range for loops, like that. Well, obviously it will fail to compile, but now let's try to do that. What range? Sorry. So basically, the range for loop internally expands to something like that. Here in yellow, there are places that user writes, and others in other colors is what compiler adds. So compiler defines some iterator that is returned from begin that is called by ADL lookup. It also defines end and do this plain for stuff in this manner. So basically also a concept, and this concept requires to have begin from us to have begin and end, and also have this dereference operator not equal and plus plus. Let's do exactly that. Okay, let's read that. We take our stuff and forward it to and create iterator from it. This is the iterator. Well, it's not exactly iterator in the STL sense, but at least it works for loops. What should we provide? We should provide the reference. We know how to do this. We should provide. So it's a typo. Please ignore this concept here. We should also provide plus plus, and we should provide not equal. For not equal, it's easy. So end will return just empty struct, and we will compare with this empty struct and return if the cursor is done or not. So this works. Now we can do this syntax, but there is one problem though. If we do that, we will have misleading compiler error. it says that junk, that there's no cursor get function, yes? And, well, why? So in order to protect this, we will add Sphinai enablers that allows us, that will choose this function only if the cursor is really cursor. I think that's it. Well, any questions?
No question? Too easy?
Yes, so.
Well, I have a couple of questions. So one is just if you can point out again the very last problem. What were we trying to solve here with this enable if? Just that.
So again, so after we defined this stuff, these begin and end functions, they will be available for any any ADL lookup in any invocation of the range for loop.
Okay.
And
sure.
well, if someone do something that is unrelated to the cursor, it will have misleading errors.
Sure. Okay. So sure.
And just we want to be a good citizen and to limit the scope.
Okay, and the other one is related to a few slides ago. We basically, at a certain point, you build this inheritance scheme to provide the right.
This one?
No, it was not. Okay.
Can you point the slide?
Okay. So.
Type erasure.
Exactly, this one. Let me just see one thing. Yeah, exactly, this point here. So here you have somehow, you have a runtime overhead, right?
Yes.
And which is due to the fact that every time is working. Okay, so pointer. So basically, every time you use the function, you have to basically have to choose the right one in the inheritance. So you have, I mean, we are paying this runtime overhead right here.
Yes. So I can explain where. So the runtime overhead will be paid here. So what happens is impl holds a pointer to the interface. So we will call this virtual method, and this will correctly. This will do lookup for the in the virtual table to find that guy.
Yeah, exactly.
And this is the overhead that we have.
And that will happen every time we use the function, basically.
Every time we call this any of the functions defined in the so any of do, get, on next functions.
Sorry, but I didn't understand. So, can you avoid this overhead
Well,
doing things differently or not? I'm a bit lost.
Well, not really, but as I explained, it's a trade-off. So you either don't use any cursor and do all your computation with the native types, but then you have to place all your stuff into the header. If you don't want, you do the type erasure. So, and you pay for it. And basically the usage for any type erasure is on the library boundaries. Like that, you have your external interface, yes? Then you want to hide the details, and you pay for it. So for std functions, so if you don't use std function unconsciously, only if you have to cover have to hide the details of the concrete types.
And if the runtime overhead is too much for you, then you have to, choose or maybe even change implementation. In the example Anton gave, you are doing language translation, so probably even if you pay an if to get the chart, you would spend a lot of more time trying to do the machine learning, for instance. Right?
Yes, in this particular case, it's peanuts. For what you are going to do, you have to translate the text. Yes, it's a complicated thing.
Yeah, which is something that high performance computing need to understand also, is the fact that performance is important, but it has a cost, and the cost of performance is that you might be ending up with a code which is extremely unflexible. So you need to trade flexibility and performance. So if you have to pay a virtual method code every time you apply your stencil function to your field, that's probably not something you want to do. But if you pay the virtual function just to call the right stencil and then the computation is super efficient, then fine, you just pay an if at some point, it doesn't matter. You don't see that microsecond, whatever, when you finally run. So you have really to be careful in when you implement your software to pay attention to what are really the parts that need to be efficient, which one that might stay a little bit more general and easier to use. Because apart from the implementation tricks here, which basically uses every trick in the book, the user interface is extremely simple and robust, and this stuff really works well.
About virtual functions, function calls, I've heard that they're not always so slow because the processor can sometimes predict. Well, I don't really know what the argument was. But, can you give any recommendations? Do you know what this, like, is there any general high performance related statement about virtual function calls if I do the same thing in a loop many times?
Do not use that.
No, but so maybe you mean that if compilers knows the in compile time the derived class that is used.
Not at compile time, but at runtime, that somehow the architecture can.
In compile time, you can write. For example, if it's you can instantiate if you instantiate derived class in the same compilation unit where you use it, so compiler may know that this instance by static analysis in principle. It may know what's the concrete derived class it is. And then there is no cost. Or it can be no cost. But here, it is used for in the context where compiler wouldn't know and because the usage of this translate function will be somewhere else in the user code, in another translation unit. And you have to use vtables.
And then you used a trick we saw yesterday also, the primary template for the type trait implementation with enable if and so on, and having a primary and some void default type. Mm-hmm. And you also used an Afanasyev that didn't need a trick that didn't need the primary somewhere else.
Okay.
Can you comment a bit on this?
Yes, it's an interesting thing. So basically, there are two idiomatic ways to use Afanasyev. First, if you want to create specialized instantiations of your class or struct, and I think I have an example. Where is it? Or maybe not. I have an example here. Yes? So we have is cursor that that have general or primary implementation that inherits from std false. Yes, and the third, and this is exactly the case for enable if that was described in our talk. And there is another case when you try to enable or disable functions based on some criteria. You should, but so I've already described mechanism, and it's slightly different. And usually, so what we can do else, we instead of having this enable if as additional parameter, we can incorporate it with the with the return value. So we'll take that, place it instead of iter cur, and replace int with iter cur. This will also work, but this form is well. This pattern is slightly more general because it can apply to, in a situation where you don't have return type, for example, in constructor.
About this last thing, do you prefer to have the enable if as a template parameter, but wouldn't it be possible to call begin with the specifying the template types and let's say altering the behavior of the thing. Like if I call begin with the current type, the cursor type, and an integer, does it change something or?
So you want to do. So am I understanding correctly that you want to do the following instead of this guy? Here you want to have so enable if here, yes?
No. My question was: is it safe to have the enable if? Is it safe at the same way to have the enable if as template parameter or as a return type? Can I call like begin with the angle brackets?
Okay, let's do it. So this is an alternative.
Okay.
Well, it works. It's the same behavior, and compilation time is a little bit faster, especially for Clang. But again, you cannot do it in constructor. So that's why I prefer the first form. Just to use the same pattern everywhere.
Other questions? So I really enjoyed Anton's talk. I found it extremely cool. I hope you appreciated the fact that we spent 2 days on very technical stuff about templates and context per lambdas, whatever. They're all in here. And it boils down that if you want to design cool interfaces and be safe, you have to know the language pretty well. And what I also liked is the fact that basically, well, the question is, how do I start doing this, right? Because, Anton's showing this, it's perfectly clear. Now you go home and say, I want to do what he did. It's going to be difficult, right? And I think one major advice, I think, is to do what we described the first day as task-driven design. So start writing what you would like to write. What is your ideal view of what you want to do? And you start writing that code. And by knowing then all these things exist, you can actually make that real. If you start from the bottom up, I think you will never get here. You will never get interfaces like this. You have to really think, how do I want my code to look like? And then work from there. And there are some limitations, right? I mean, do you want to use the pipe interface or not? I mean, the pipe, if you use the pipe, you need to put it into a namespace, otherwise other codes might get in some issues. So, I mean, you have also to, try not to, at least when you start, not shoot for the stars, but shoot for something that makes sense, and then you can work out all these things. But it will take time. I mean, it will take time, experience, and errors. But I find it extremely cool.
Yes. One thing that I forgot to mention so I'd like to do more stress on the concept. So it's very important that you clearly understand what you want to be. So what class are you accepting for the template parameters? This basically probably this talk. So so my intent was to teach you think about the concept, because this discipline is required if you do the generic programming. This is how the good generic libraries are implemented, including STL. You cannot just write template code just test it for one or two random classes that can be instantiated with that particular template. Otherwise, you will get into trouble, because you will never understand what are concepts in your application that you have just written. It happens that the code works, but you don't understand it. And one more thing. Well, so conceptually, what we do here? So we just make our we transform one concept into another. Yes. So we have to we basically model the concept that is required for range book. Wait, sorry. Oh, it's annoying. Where is it? That is required for range loop, and we just implement it on the top of other concepts. So we get one concept, we model another one. Yes, and also moving a little bit back. We have this pipes syntax sugar and compose functionality. And note that this doesn't basically the only thing that the concept for the arguments of the compose is just the functions, nothing else. And for pipes, it's also just functions. Yes, we don't limit ourselves to our particular concept, that is a function from cursor to cursor. Yes, and this is important thing to understand, that that the concepts are richly composable. One concept can consist of several concepts. It's just a composition of them. Yes, and it can be split. It can be used together. So it's even more flexible than the inheritance model of the object-oriented programming. Thank you.
And what is also cool is that those two slides that Anton just shown is the actual code. It's not just a code, this snippet that shows, well, this is where the code will look like. This is actual code. This is all code you need. It's pretty amazing. They fit in a slide each. So it's really, really cool. Concepts also, as you might know, are something that C++ Standard Committee have been trying to put into the standard for many years, since C++ 11, actually. At that time, there was a concept of concept maps, where you could actually do the mapping between different things. And they were removed early on because they were a little bit too powerful, because you could basically you could encounter problems which are undecidable. So there's nothing you can do about that. But finally, C++ 20 seems to have concepts finally. So they've always been removed at the last meeting. But the concepts offers you a way to really do this kind of work where you, in a more formal way. So you can define concept for your class, and then you can check that a function takes something that models that concept. And it's going to be pretty cool, actually. But yeah, this will only be available in C++ 20. But this technique developed along the years. Basically, the concepts that are being proposed for standardization basically tries to learn from these things and put these things into a formal way, into a formal tool that you can use. So I guess we can go for lunch if there are no other questions. Last second. All right then. Thank you.